Chips today burn too much power, and excess power consumption prevents chip designers from incorporating additional functionality and capabilities. To get past this power problem, the industry must rethink every aspect of electronic design, including the structure of the transistor. For many years, transistors have been stuck against a supply voltage wall of around 1 volt. Since power is primarily a function of voltage, reducing power means we must find a way to reduce the supply voltage. Looking at a conventional transistor, the primary reason voltage doesn't scale is variability in threshold voltage, or VT, which gets worse as transistors get smaller. A primary cause is random dopant fluctuation in the transistor channel. Even with small differences in channel doping, threshold voltages can vary dramatically from one transistor to another. With billions of transistors on a chip, VT variability becomes a big problem. Traditionally, designers compensate for VT variability by using a supply voltage that is high enough to turn all transistors on and off cleanly. But this voltage overdrive wastes a tremendous amount of energy. To get past this power roadblock, the industry needs to rethink the CMOS technology that has driven the industry for decades. But what if it were possible to reduce the power in planar bulk CMOS? Suvolta has invented a device technology that does just that. Suvolta's deeply depleted channel technology, or DDC, reduces threshold voltage variability and enables continued CMOS scaling. In a typical implementation, the DDC channel has several regions: an undoped or very lightly doped region, a VT setting offset region, and a screening region. The undoped or very lightly doped region removes dopants from the channel, which allows for a deeply depleted channel. This reduces RDF fluctuation, which allows for VCC scaling and improves mobility, resulting in improved effective current. The VT setting offset region sets the transistor threshold voltage levels without degrading channel mobility. This region also improves sigma VT over conventional transistors. The screening region screens the charge and sets the depletion layer depth. It also serves as a body for dynamic VT adjustment through biasing, if desired. The DDC transistor has a much tighter distribution of threshold voltages. As a result, chips designed using DDC transistors have 30% VDD reduction with no performance impact, much lower leakage, less design guard banding, and improved yields. In addition, DDC transistors allow for the setting of multiple VTs, which is vital for today's low-power products. Besides the benefit of significant VT variation reduction, DDC transistors display increased channel mobility for increased drive current, reduced dibble, and increased body coefficient for better VT control, all of which lead to further reductions in power with higher speed. Perhaps the biggest benefit is in embedded SRAM memory blocks. For most chips, lowering supply voltage is limited by the SRAM. However, with the DDC transistor, conventional 6T SRAMs have been demonstrated operating below 500 millivolts. This is significant as it is amongst the lowest voltage ever reported in a standard embedded SRAM. With all of these benefits, one might wonder if DDC is challenging to manufacture or costly to adopt. In fact, DDC technology is compatible with existing manufacturing and design flows, manufacturable in existing fabs, integratable with existing CMOS processes, and compatible with legacy design IP and EDA tools and flows. The cost advantage resulting from this compatibility is significant, especially when the DDC transistor is compared with alternative advanced device technologies. The 1-volt wall, the power wall, the cost wall. Huge barriers all now overcome with Suvolta's DDC technology.